Okay. What's up? Welcome back. Happy Lag BaOmer. I'll be teaching this 2 hours today, continuing what Jonathan was doing on Thursday. So we're studying the hot field network with the finite gain or finite temperature regime, if you recall. We have our usual set of equations, and as you remember, we have a finite beta in the Fi curve of the neuron. Our transfer function, the transfer function, the tangent hyperbolic. So we have a finite gain in the transfer function. So we studied, right? You guys studied first the case of beta, the infinite beta, where the neurons are effectively binary units, and calculated the capacity under that limit. And now we're interested in studying the hot field network with finite beta, finite gain, for the physicists, finite temperature, non-zero temperature. And what Jonathan already did last week was the example that's still here on the board conveniently, where we take our network and put in just a single memory pattern, and then we found that we could study the dynamics conveniently through this overlap parameter. So we defined the overlap with our memory pattern. In that case, last week we only had a single memory pattern, so we studied basically the dynamics of a macroscopic, what's called an order parameter, a macroscopic parameter that describes the statistics of the system, in this case, just relative to the memory pattern that we're interested in. And we found that we could study the dynamics of this parameter, and therefore study the characteristics of the fixed point, basically just already relative to what we're interested in, which is, does the system have some kind of relationship to the memory patterns or not? Does it have significant overlap with the memory, i.e., what's the value of M1 in this case at fixed point, and when are the fixed points stable? So that's what we did on Thursday. Yeah.
So in this case, we talked only about a system with one memory.
Yeah.
But it's not enough for us.
Right.
Because the system has more memory.
Right. It's not very interesting to build a whole network that just has a single memory pattern. So now we're going to expand that a little bit. We're going to expand it and just go for 3 memories. Not too ambitious yet, but just kind of to get us a qualitative sense of what goes on, we'll expand to 3 memory patterns. Okay. So store 3 memory patterns. Okay. So we have our Jij. It's going to be the usual 1 over n. In this case, mu, the memory pattern, goes from 1 to 3. Pi mu, Pj mu. Right? And Hi, of course, as usual, the input onto neuron I. So we come over J, Jij, Fj. And just putting in our definition, as we've done numerous times already, putting in Jij, the structured connectivity matrix. Sum over J. So again, we can be like Jonathan was being last week, being careful about the J. We do this for J not equal I. So we can, but like Jonathan discussed, that winds up being negligible. So we wind up ignoring the particulars of the J not equal I, but we can keep track of it for now anyway. So we have Pi mu, Pij, Fj. Again, we'll just do as we did before, rearrange the sums, pull out the sum on mu out front, and the Pi we can pull out because after that we'll only have a sum on J. So Pi mu, and then 1 over n, sum on J not equal I, Pj mu, Sj. And this, of course, as we did with Jonathan, once we rearrange these terms, we can recognize the term here inside the sum as almost being identical to the overlap with memory pattern mu, m mu, right, up to that single 1 out of n terms, which we'll ignore.
You have a j there instead of a mu.
That should be j, and that should be mu. Okay, so finally, we get as the entire input to a single neuron is the sum over memory patterns, pi, that neuron's state for a given memory pattern mu, times the overlap with each memory pattern. So each memory pattern is contributing to the input of every given neuron according to the value of that neuron at the memory pattern. That's the input. Approximately, I should be, to be careful. That's approximate. And now we can do what we did before, what we did over here, looking at the dynamics of the overlaps. Here we only had one overlap. In this case, we're going to have more than just the one overlap, but we can do effectively the same thing. So we recall this definition of the overlap with a given memory pattern, and then take the derivative of that in order to write the equation for the dynamics. So we'll write m dot 1, the dynamics of the overlap with the first memory pattern. All right, and it's just taking the derivative of that definition, pi mu s dot I, and then just plugging in the equation for the dynamics of si. So let's go ahead and do that. 1 over n, sum over pi mu, and then we have a minus si from the dynamics. And then we're going to have another term. Sorry for the crowdedness here. Have another term, pi it should be 1. Thank you. For now, we're looking at specifically the first memory pattern, so that's 1, and also here 1. And tangent hyperbolic, beta, hi. Of course, the first term here is just minus m1. And now this is the term that's going to be of interest for us. So let's see what we do with that. So we have m dot 1 equals minus m1. And now let's plug in hi, the input into neuron I, from what we calculated up here. Okay, so we have minus m1 plus 1 over n, sum over I, pi1, tangent hyperbolic beta, and then sum over the different memory, over all the memory patterns, in our case from 1 to 3, pi mu, m mu, the overlap parameter. Okay. So let's look at this term. We have to try to make some sense of this term. We have a sum over n, 1 over n outside, and then we have this pi associated with the memory pattern we're interested in, and then inside the sum over the different memory patterns. Okay. Now, what did we do previously? Previously, when we only had one memory pattern, we had a similar term. And now we noticed something over here. We noticed that each pi is either 1 or minus 1, and it appears inside the tangent hyperbolic and outside the tangent hyperbolic. And so Jonathan pointed out that if you have some plus or minus 1, call it z, tangent hyperbolic zx, because tangent hyperbolic is an odd function, if z is either plus or minus 1, this is just equal to tangent hyperbolic x, right? If we have some z, a random variable that's either plus or minus 1, then changing the sign, so effectively effectively what we can do is if we can change the sign of what's inside the parentheses of the tangent hyperbolic together with changing the sign outside and keep our term without changing the value of the term. So z tangent hyperbolic zx is just the same as tangent hyperbolic x for any z that's either plus or minus 1. And so I'm going to use that as a trick here. Right. So what I'm going to do is that means that what we can effectively do is multiply the pi that appears outside the tangent hyperbolic. We can multiply it inside the tangent hyperbolic. And so I'm going to do that as a trick. One doesn't have to do that for the next step, but it just makes things a little simpler. So this term, I'm going to multiply pi1, which is either plus or minus 1. I'm just going to multiply it inside the parentheses. Now, pi1, so I'm going to get something like this. So I'm going to get pi1 squared m1. pi1 squared, of course, is 1, regardless. That's going to be just 1. And then I'm going to get pi1 pi2 m2 plus pi1 pi3 m3. Okay, so that's the term inside our sum. And then, of course, we have 1 over n, sum over I. Okay. Now, what do we do with this whole term? So this whole term, 1 over n times a sum, is some kind of empirical average, right? We have a randomness. We have these random variables, pi, which were our memory patterns. We sampled the memory patterns from the beginning as a set of random variables, and then we wind up with some term that's 1 over n, a sum over something. So that whole sum term is effectively an empirical average so all this is the empirical average of the tangent hyperbolic So what's an empirical average? We have a random variable, and we sample from it some number of times and take the average. That's an empirical average. Now, it turns out, in our calculation of the overlap, we get a term that's effectively an empirical average. We sample over all the neurons. We think about the memory pattern, the value of the memory pattern on each neuron is a random variable, and however number of neurons we had, we've effectively calculated an empirical average of this function here, beta m1 plus pi1 pi2 m2 plus pi1 pi3 m3. We're effectively calculating here an empirical average of this term. And now, so as a reminder, if we have a random variable xi independent, so the empirical average, 1 over n, sum over I, xi, we know that for large n, it's going to approach the real expected value. Call it x bar. And there's going to be some kind of deviation from the expectation, which has order of magnitude 1 over square root of n. Right? That's a central limit theorem. And the reason for the scaling 1 over square root of n, also as a reminder, we can look at this term, look at the variance of the entire empirical average, right? The variance of a sum for independent variables is the sum of the variances. So we pull out a 1 over n squared outside of the variance, and then we just have the sum of variances of individual xi's. So as long as the xi's have finite order 1 variance, we get the variance of the empirical average is 1 over n squared times the sum of n terms that are order 1. So the variance is 1 over n, and therefore the standard deviation, the typical value, is 1 over square root of n. So the typical deviation is 1 over square root of n, and that's going to be important to us. Okay, it means that when we have here the empirical average, the sum over 1 over n times this whole tangent hyperbolic, we can replace that effectively with the expected value of this term, plus a deviation that's small.
Under which assumption? That n is big enough?
Under the assumption that n is big enough and that these PIs are independent for different neurons.
The m's are not independent. Are they? Because they are...
The m's are dynamic variables. The m's are dynamic variables, not random variables.
But you're studying things that are not independent, and they're part of the sum, and they depend on polymorphs.
Right, but they depend on the value, the activity patterns of the neurons, and we're writing the dynamic equations for those m's. So as far as taking the average is concerned, when we take the average here, like m1 is and m2 and m3 are some constants inside this term. We take this average and we have some constants in there. So we're taking the expected value of this as a function of m1, m2, and m3, right? When we have some given value of m1 and m2 and m3, this will give us some term expected value, and this empirical average will give us something very close to that expected value with a deviation of 1 over square root of n. Now, I should point out that this is specific to the case we're looking at now, where we only have three memory patterns. If we had here a large sum, if we had p in the range on the order of magnitude of n inside the sum of the tangents hyperbolic, so here we didn't stop at m2 and m3, but we had a large set of p also approaching and random variables inside, then effectively the variance really will wind up being proportional to p over n. So here we're looking at the specific case where p is finite and n is in the large in the large n limit. So everything we're saying here is going to be true for finite p and large n. Once if we try to load in more and more memories, then we're going to run into problems. It's effectively always p over n, but here we're taking a small p equals 3, so we're not interested in it. Okay, so about the m's. So I mean, if we look at this term, as far as this sum is concerned, these dynamic equations that we're writing are legitimate equations for any value of m1, m2, and m3. We're going to wind up with a system of three variables, dynamic variables, they're going to be interdependent on each other, their dynamics, and so on. But this sum is going to have some value for any possible values of m1 and m2 and m3. As far as the sum is concerned, those are constants here, and what I'm saying, just by the independence of the PIs as independent random variables, this sum for any given m1 and m2 and m3 is going to be very close to the expected value of the tangent hyperbolic with the same constants, m1, m2, m3. And then there's going to be a different value for as m1 and m2 and m3 change, this term also changes. So we're going to have this as a function of m1, m2, and m3. Okay. So let's look at this. Let's look at this term. We have m1 and we have pi1 and pi2. Each of those is either plus 1 or minus 1, and they're independent, and 50 with a probability of 1/2. So this term is either going to be positive or negative, with a probability of 1/2, plus 1 minus 1. And this term also, pi1 times pi3, can take on the values of plus 1 minus 1, with probability 1/2, and independently of the term before it, right? So there are 4 different terms in the average, and they each occur with equal probability. So let's write it out. We have beta m1 pi1 pi2 m2 plus pi1 pi3 m3, and it's going to be equal to 1/4 times the sum tangent hyperbolic beta m1 plus m2 plus m3 plus tangent hyperbolic beta m1 plus m2 minus m3 plus tangent hyperbolic beta m1 minus m2 plus m3 plus tangent hyperbolic beta m1 minus m2 minus m3. So that's the expected value of this tangent hyperbolic term, right? We have kind of positive contribution from m1 every time, but we're averaging over the different possibilities. You can think about the m2 and m3 relative to m1. They have a randomness that's given by the potential overlaps between the actual patterns themselves, the pi1 and pi2. So they contribute in kind of random ways relative to m1 in the input. So this whole term, I'll write it like this: 1/4 the sum, and I'm going to introduce just kind of labels z2, which is plus or minus 1, and z3, which is plus or minus 1, and write this whole term, the sum over 4 terms, just as m1 plus z2 m2 plus z3 m3. Again, z2 and z3 are just counting through the different possibilities of plus 1 and minus 1, different contributions. Okay, so this is the empirical average, and therefore we can write our final equation for the dynamics of m1 as m1 dot is minus m1 plus this term that we calculated here, 1/4 sum over these different contributions, plus or minus 1, tangent hyperbolic beta m1 plus z2 m2 plus z3 m3. And we should remember we have some order 1 over square root of n term that the equality is not exact.
I think the beta of what?
Like that? Here too? Yeah. Yeah. Okay, so that's the dynamics of M1, and we can similarly calculate identically effectively the dynamics of M2 and M3. So let me write those for the sake of completeness. So we have m2 dot minus m2 plus 1/4. Now the random contribution is going to be from z1, kind of from m1 switching signs and m3 switching signs. We have m2 plus d1 m1 plus d3 m3. And similarly for m3. M3. Okay, so we've effectively reduced our dynamical system of n variables into a reduced system of 3 macroscopic quantities, which are the overlaps with the 3 different memory patterns. And we can kind of start to intuit how we would extend this in principle for any value of p. We would start to have to be careful if p reaches the order of magnitude of n, because the additional deviations from the expectation value will start to be large. But at least for finite p, we can extend this to any number of p, and we'll have p dynamic variables that represent macroscopic quantities that we're actually interested in, which are to what extent is our system in overlap with a given memory pattern. Right, now we can start to ask questions of function. Does the system work in the way that we want it to work? Right. So, in particular, we want the system to perform associative memory. And we want to know, for example, does the system perform memory recall? Can we start the system with some non-zero, but not very large, overlap with a given memory pattern? And will the system converge to a more full recovery of that memory pattern? Will converge to a fixed point where the overlap of that memory pattern is substantial. Okay, so okay, associative memory recall. So let's set an initial condition where Si of 0, let's align the activity state with the memory pattern number 1 for some large number of neurons, for some substantial fraction. For I equals 1, 2, all the way up to some substantial fraction of n. So for q less than 1, let's set memory pattern aligned, the activity pattern aligned with memory pattern 1. And then for all the rest, let's just assign it randomly. So Si is plus or minus 1 at chance for I larger than Qn. What? Is anybody taking notes? Yeah? Great. What's your name? Idan. Great. Thanks, Idan. Okay. So that's our initial condition. We're aligning the activity pattern with memory pattern number 1 for some significant fraction of the overall neurons. And then the rest we're going to take randomly. So let's calculate M1, the initial value of overlap with memory pattern 1. That's just by definition 1 over n, sum over I, the memory patterns Pi, Si initially. And we'll split this naturally into a sum 1 over n of those first neurons, which we know are for sure aligned. I equals 1 to Qn. And for those neurons, we have Pi, Si are identical, so that's just 1 inside the sum, and then we split off the second part of the sum, 1 over n times the sum from I equals qn plus 1 up until n. And here we have pi1 si0, which is going to be aligned or unaligned plus 1 and minus 1 at random. So this term we're summing over qn terms times 1 over n. So we're going to get here q. This term we're summing over n minus qn terms, which are random, plus or minus 1. And we have 1 over n out front. So that's going to accumulate with some kind of random alignment, but because of the independence of those terms, it's going to give us something that's order 1 over square root of n. Okay? So essentially our initial overlap is q. That's how we're building our system. And now we would like to see how this overlap progresses in the dynamics of the system. Right?
What happens to the right?
The right-hand sum? It's just summing up random contributions plus or minus 1. So the net sum of those is going to be on the order of square root of n, and then we're dividing by 1 over n out front. So its contribution is going to be small. We're assuming here that q is a fraction, but a finite fraction, not a very small fraction, an order 1 fraction. It could be a third, it could be a half, something like that. And now, okay, so we want to know how the dynamics of M1 are going to propagate through the system. Of course, that's not enough. We have effectively a 3-variable system, so we need to know also the values of M2 and M3. So M2, at the initial state, we're going to sum over all neurons and take pi2 times the initial state of neuron I. Right? In this case, Si was chosen totally independently to the memory pattern, to the second memory pattern, right? Because either it's defined explicitly as random plus or minus 1, or it's given the value of pi1, but pi1 itself was chosen randomly, independently from pi2. So here we just have a sum over n random contributions plus or minus 1. So this whole sum is going to be something on the order of 1 over square root of n, small relative to q. Okay, and the same thing for the initial overlap with memory pattern 3. Right? We're just starting off at random, so it's going to be, with regard to the memory patterns 2 and 3, the initial condition is effectively random, and therefore small overlap, 1 over square root of n. Because right, M1 we're choosing that some large number of patterns, number of neurons are for sure lined up with that. That's the one. Right? We're lined up with memory pattern 1, but not completely, right? To some extent.
Isn't it assuming that the memories are very different than one another?
Yeah, right. Absolutely. That's a crucial thing, like in this whole model. The whole model assumes that the memory patterns are very different from one another. Why? Because they're chosen at random independently. So they have some fraction of possibilities that some of their neurons may be aligned, but it will be only a very small fraction of them relative to the large n.
So how do you take into account the possibility of the memories being randomly very similar?
Well, they'll
Many neurons?
Yeah, just very neurons. We just have a very large number of n neurons, and choose the memory patterns independently, and so then the probability that they're very aligned will be very, very small. As an aside, it's interesting to consider different alternatives, different kinds of memories where maybe memory patterns have some kind of intrinsic relationship to one another. Right? Like if we think about memory in an everyday kind of real world way, we have memories that are similar to one another. We might have hierarchical structures of things. We generally remember our elementary school, and then we look closer to finer details of specific days of elementary school and so on. So there's an actual intrinsic structure in the memory pattern. So one of the structural features of the Hopfield model, and one of the reasons that it works very well, is because we specifically choose memory patterns that are not structurally related at all. They're totally independent, so they're almost as orthogonal as possible. Okay, so we have these initial conditions. We're checking out what happens when we align our memory partially with one of the memory patterns. What will happen to the dynamics, which we wrote over here. Okay, so let's see what will happen. Right, we would effectively, like, we have these three equations with three dynamic variables, starting with these initial conditions, and so we want to see it how they're gonna propagate in time. So let's look at these three different equations in this specific case. So we can look, for example, at time 0 at m1 dot, which we're starting with our initial condition of q. So we have 1/4 the sum of these four different possible terms, but only the m1 term is order 1 term, and it starts out with a value of q. And these m2 and m3 at the beginning will give small contributions, right? Okay, so we have four different terms. Each one of them has an order 1 contribution of m1, and then a term that's negligible inside the tangent hyperbolic. So we can approximate this. We can essentially kind of use a Taylor expansion. We have a small deviation here. Hold on a second. So we can essentially take out each one of these terms is close to tangent hyperbolic beta m1 plus something outside the tangent hyperbolic that's also of the order 1 over square root of n. Yeah.
Shouldn't it be like a function of the whole time? Like it shouldn't be like the only initial condition, right?
Yeah.
So how do you know if the m2 and m3 terms are going to be much
if they're going to grow? Right. So it's a crucial thing I need to check also that I'm starting with m2 and m3 small. I have to check that those are going to stay small.
Yeah.
Or hopefully even get smaller, right? So we'll do that in a second. Maybe I should have started with those, but we would start with m1. So assuming that m2 and m3 are small, we can approximate this. Each term is just tangent hyperbolic beta m1 plus some small contribution, and we find that on the whole in that case m1 dot is approximately minus m1 plus tangent hyperbolic. We have 1/4 times 4 terms. So that's just tangent hyperbolic beta m1, right? That's exactly the equation that we've seen a number of times. We saw it in the case where we only had one memory pattern. So in this case, if the overlap begins in a state where it's small relative to m2 and m3, then dynamically, at least as far as m1 is concerned, it's like they don't even exist. But we have to check, what, remind me your name? Itai. We have to check exactly what Itai said. What about m2 and m3? How do we know that those actually stay small, not just their initial condition? So we look at the equations for m2 and m3. And at least at the beginning, right, m2 and m3 are small. And m1 is not. So we have a contribution of z1, where z1 is either plus or minus 1, sum over z1 plus or minus 1, m1. And then some contribution that at least at the beginning is small, some order 1 over square root of n terms. Again, using the fact that this term is small, we'll effectively do a Taylor expansion and approximate each one of these terms as tangent hyperbolic beta z1 m1 plus some small deviation from that. Okay, now we have 4 terms where 2 of them have plus m1, and 2 of them have minus m1, right? And divided by 1/4 outside. So just to write it out for concreteness, we have m1 dot is approximately equal to m2 dot approximately equal to minus m2 plus 1/2 tangent hyperbolic beta plus m1 plus tangent hyperbolic beta minus m1. Of course, tangent hyperbolic beta minus m1 is the same as minus tangent hyperbolic beta m1, right? Tangent hyperbolic is odd. And then some additional 1/square root of n terms that we haven't calculated, right? So effectively, this term is going to be 0. The leading contribution, dominant contribution of the input onto m2 is going to be 0, and we get something m dot 2 is approximately equal to minus m2, and it's got some 1/square root n order terms. And so this shows us exactly what I was asking about. If m2 begins as small, it's going to just simply decay. And the same will be true for m3.
It stayed the same actually, no? Because
It'll probably stay the same order.
stayed 1/square root of n.
It
Started at
probably
magnitude.
it probably will remain that order of magnitude if we checked it. Yeah. Yeah. So therefore we have a consistent picture of what will happen if we begin with some finite fraction of neurons aligned with a given memory pattern, m1 in this case. The dynamics of that memory pattern will lead to a fixed point, which we didn't explicitly talk about, but we've seen the fixed point equation for these dynamics plenty of times. So we have a fixed point, which will be non-zero substantial fixed point. Its actual value will depend on beta in ways that we've seen before, and m2 and m3 will stay small. So this shows us that associative memory recall works. If we kind of remind our system, give our system a gentle reminder of one of our memory patterns, it'll recall maybe not the full memory pattern, right? If beta is not infinite, then it won't come to a state where m1 equals 1, where all the neurons are aligned with the memory pattern, but it'll be a substantial memory recall. Yeah.
How do you know that m2 is always larger than the order?
The m2. Well, so it's not larger. In fact, right? We said m2 is of the same order of magnitude, but the point is that it stays small. It stays order of 1/square root of n.
And if this change is positive, then for a long time it will not.
If you're saying like if randomly this was going to be larger, maybe it could accumulate. That's an interesting question. Like right now m2 is order 1/square root of n, and we have some additional contribution that's also 1/square root of n. This could be larger, kind of just by the randomness, and it could potentially make m2 grow. I'm not sure that we can rule that out.
It has to depend on Q somehow, right? We don't see any dependence on the Q there. If Q is small, then all of this doesn't work and falls out.
Right. Yeah. Right. I mean, if Q is small, then we can't make this separation. Really, right? If Q is order 1/square root of n, then this is kind of washed out to the noise, also. Yeah, it's a good question. What will happen next? And probably there's some chance. There's some chance where you kind of fell in the wrong possible overlap, and even though you started with a small m2, you might by chance fall in a state where it will actually grow. I'm not sure off the top of my head how to rule that out. But the typical behavior will be one in which it'll stay, m2 and m3 will stay small.
Is there a threshold Q at which you get
That's also a very good question. Is there some kind of finite fraction Q? I don't know. I'm going to answer that. So look it up.
I mean, at the beginning, you also draw like the value of the fraction. Can you define them?
Right.
I mean, your
Right.
initial.
Yeah, there is work on that. I can check the literature to see what they say on that. Some of the questions will be like, will it be a critical Q where it just breaks down and before that we're totally safe, or will it be like, well, there's always some small probability of having one of the other overlaps grow, and just that probability will grow smoothly, or will it grow suddenly at some critical point? I'm not sure the answer to that. Okay, so that's one at least good thing. We've left some questions open that we're not necessarily sure about, but at least typically what will happen if we start with some non-zero substantial overlap with a given memory pattern, so we'll reach a solid fixed point, and we can call that kind of a memory recall. But what we'll see in the second hour is that we're not done here. We have to also consider the possibility of different kinds of overlaps, and specifically we'll look at mixed states, what are called spurious states, where the initial condition might be some weird combination of the different memory patterns, and we have to check those things. We don't really want to be able our system to remember kind of weird combinations of like of one person's head mixed with a different person's body or something like that. So we'll see whether our system may accidentally learn to have those also as memory patterns, as stable states, or not. כן, בהתחלה, בדיוק. כן, בדיוק, כאילו להכיר אותך. ואז, association, חשבתי על זה.
מה יהיה משהו כמו כזה, לא? שכאילו גדול לא, QN זה מספר כאילו המספר של האלה שיהיו אותו דבר, נכון? כן. ואחד חלקי שורש N זה מספר כאילו כדי שהאיבר הזה פשוט יהיה מסדר גודל של QN, נכון?
מספיק לי שזה יהיה סדר גודל, שזה יהיה אז
באמת, רגע,
נראה לי גדול והרבה מאחד. השאלה טובה היא לגבי דברים האלה.
זה יותר פשוט, כי הדבר הזה הוא בסדר גודל של שורש של QN, זה אפילו תנאי יותר פשוט. זה מה שאני מתכוון, אתה מציע Q יותר מדי.
זה סדר גודל כזה.
זה מה סדר גודל?
M1 זה Q.
M1 זה Q. אוקיי.
השאלה יותר קשה, מה מבטיח שזה
זה יהיה עד שורש חד הוא יהיה סביב האפס, הוא יהיה סביב האפס, אבל כמה רחוק זה לא משנה, העניין נראה לי כשמוציאים מוואי שם זה נהיה בריבוע זה נראה לי מאוד משמעותי כן, נכון או מלמעלה עשינו את זה מהכל, אז זה יוצא לנו בריבוע וזה כן, זה הממוצע של זה אפס, אבל עדיין זה משנה לא? אם זה פלוס או מינוס פה, הפלוס הזה? לא מעניין, זה סדר גודל פעם מעל או פעם מתחת. נכון, אבל אני יודע שזה משחק סביב זה לא משנה. זה איבר קטן של הדרך איבר גדול. משהו שם. לא מעניין, זה מבחינתי אחרי זה מוצר, מודיעים את זה אפס ולהתעלם את זה.
תיאוריה זה לא מעניין.
כמו שאנחנו מכירים את ה...
טוב, אבל האמת שזה לא כל כך בהשתברות כאילו לא יודע שם עושים דברים כאלה. לא מזניחים דברים ככה פה. זה
אני לא מבין איך אתם יודעים מתי זה להזניח, מתי זה לא זניח.
צריך להיזהר, כי באמת פה ברגע שאנחנו נרצה להכניס יותר memory patterns, זה לנו בעיה. כל הזמן
אתם עושים תורה חופשית מאוד בהזנחות. כאילו מרגיש לי, אני כזה עוד לא קלטתי מתי
כי M זה מספר רציף בין 0 ל-1, נכון? אז M בריבוע זה גם קצת יותר קטן. הוא עדיין אבל...
אבל איך עדיין זה מספיק יותר קטן?
כי ה-O זה 1 חלקי M. אוקיי, 1 חלקי שורש M. זה מספר מאוד מאוד קטן. זה כאילו, איפשהו ליד ה-0. זה אפילו בין 0 ל-1.
כי איך אתה יודע מה מספיק קטן כדי להיות זניח? איך אתה יודע
זהו, אז אני...
10 חלקי מינוס 30 זה זניח.
כי השאלה מה יש לידו.
אז כאילו אם הייתי עושה את זה...
10 חלקי 30 גם...
בדיוק, אז הייתי ממש בזמן.
10 חלקי 30, אנחנו מדברים על חצי, רבע, שליש, זה זניח.
אני כאילו לא עשיתי את זה כי מה שהיה שזה בסדר גודל של M1 order 1.
שיש לך כאילו...
נכון, זה לא שבוע, אז אני לא רציתי להכתיב את זה. הייתי יכול להכתיב את זה בזמן אפס, ולהגיד אוקיי, בזמן אפס אני יודע שאין דעת.
שיעור על המחשב, כן, זה די גדול.
אבל אני רוצה לקשור על הצורה של
לא, האלף,
הדינמי.
זה
משתנה, זה רק מה שאני מבין. גודל של 1, לעומת M2.
1 חלקי 30.
אני יודע ש-M1, order 1, שזה הרבה יותר גדול מ-M2.
עוד פעם, הם יכולים
להגיע
להגיע
לסדר
לסדר
גודל, רק להגיד, אוקיי. רק מניח ש-2 order 1.
גם בדרך כלל הם להיות יותר גדול אלף זה כאילו אולי במשהו חלקים במחשב גדלים, אבל במוח, כאילו הם מיליון.
כן, אז זה כאילו...
לא, אבל כשאנחנו מן הסתם נעשה אין גדול, אני יודע שהוא גם נפריד את העניינים.
יהיה קטן.
כן, אבל השתרגל מכל.
אז שם, כן, אותו משחק, ה-M1 הוא הדבר הכי שנשאר פה שהוא לא קטן, והוא מופיע פלוס ומינוס.
לא השתכנעתי, לא השתכנעתי על ה-M, כאילו... לא,
על מה?
על זה שזה, כאילו רלוונטי ברגע שיש תלות בין דברים שהם נמצאים בחיים.
אבל איזה
כאילו אתה אומר, אני זוכר על נוירונים, ואני יודע שנוירונים הם תלויים, אז אני יכולה...
נכון, אבל מה לא סוכן כל הנוירונים? לא סוכן על הפעילות של הנוירון. פשוט PI, זה משהו שהוא לא עושה לזה שום דבר. בסדר, אבל אני משאיר את זה כמו שאני לא מתחתיה, זה מספר. תגידי לי מה המספר, אני אכתוב אותו פה, אני לא נוגע בו בכלל. מה שאני סוכם ומה שאני מנסה עליו זה הדברים האלה. זה אקראי, וזה לא תלוי.
אני לא מבינה למה פה זה שונה משהו.
כי פה אני סוכם על R. יש לי N, 3N משתנים מקרים, וביחס לסכום הזה, N2 הוא משתנה קבוע.
אני לא מבינה למה זה...
כן, אלגבראית, כאילו, כתבתי משהו פה, אפילו ב-I, הוא לא משתנה. הוא זה, תגידי פה 2, 4, חצי, לא משנה מה. הוא מופיע בכל אחד מהאלמנטים בתחום. ורק זה אקראי וזה לא תלוי בזה. זה כן חשוב. זה חשוב שזה לא יהיה תלוי בזה. אם זה היה פה איזה משהו שהוא אקראי, אבל יש לו איזשהו תלות בפנים, אז זה נכון. זה המבנה, זה אני התחלתי שלו.
כאילו כתוב כאן הרי, סתם, כמו הקלאסית, בטוח אומר שזה בוקר שזה בכל העולם. ברור שתיקח מים ותחילה, זה שורש מהמתנה.
אם זה...
לא יודע את מה שלו. שאלה לא, נכון, אני חושב שסתם, אני חושב שסתתי על לפני, אמרתי וואי, שבי יוצא לי כזה. אגב, שביותי זה בדיוק בצורה אדיר, אני חושב שביותי אגב, אחד הדברים שבאמת לא מבין, איך שאנחנו לא רואים וגם, אני לא יודע אם לא חייתי איזושהי שאלה כאילו, חייתי איזושהי שאלה מה היה, לא אבל לדעתי היה אבל כאילו, כן יש שם סיפור של טיורינג, לא היו 4 מודלים שונים חשוב, הוא איכשהו כזה איזשהו קרב, אחד מהארבע וריאציה על יש גם עובדה שאתה אומר, יש לו איזשהו נוראים של עובדות, בצורה מאוד מאוד חכמה, בצורה שהיא לא יכולים לתכון טיורינג של זמן תקמה. הם עדיין שקולים לא אומר שזה לא מדע לי. לא, סתם כאילו, הרעיון הכללי שאמר שמונה בצורות על העצבים, נותן לו להיות במצב של קסע, שזה נותן לו לפנים שלו, ואז בעצם זהו, אבל כאילו, אבל בהרבה מובנים זה עובד משנה את התחלה יותר טוב מזמן, אבל לא שטוב, לא תמיד זה אבל כאילו ואז יש שאלה, אז מה? כאילו זה פשוט אומר שסיפורים זה לא הכל, זה לא משנה את זה. העובדה שאתה לעשות את זה, כאילו נורא נוח אבל להגיד אוקיי, זה אומר שטיורינג זה לא יכולים לראות לי ספורים, אבל משהו בהם מרגיש לא שווה. אני מרגיש שזה לא כמו שטיורינג עובדה לך, מה זה מה שמגיע לך? ושאלה במידה זה משהו שאומר שהאלגוריתם לא נתן הלומד כמו כל בלי לחלוטין מהאלגוריתם, אתה לא מכיר אותו בכלל. עכשיו, כל האנשים שהם מאמינים על שסתם מים, לא ברור להם על שסתם. סתם אינגלציה, זה נראות, ולכן זה כמו גדול, אתה רוצה ליצור את המשקלות שהשגיאה שלך היא בעצם, לא משהו שאתה לא מבין. אבל עדיין יכול להבין בדיוק, כמו עובדות, אתה יכול, באופן קונצפטואלי, להשתמש בעבודת מחשב, אתה מייצר מכונת טיורינג קונצפטואלית שמריצה שטיורינג. תכנית אינפוט, תכפיל את ה-weight, זה עדיין מרגיש לי משהו אני מבין אבל שזה לא אותו דבר, אבל בסוף אחד מרגיש את השני, וזה נורא מתבקש כאילו
וגם את בטח כאילו, לא ראיתי משהו כזה, זה בטח כזה, כי עשינו מישהו אחר.
אני חושב שבאמת, ובאמת יש לי משהו, אני חושב שאני ממש מוכר. ההבנה התיאורטית, ממש ממש מוכר, כאילו שאיזשהו מספיק, אנשים משתמשים בזה לא מבינים
אמרו לי לספח את זה, כאילו, לאמת על המוות
זה לא
Okay. All right. So let's keep going. So I said we're going to now study how this system, the hot field model in finite gain, deals with spurious states. So let me give you an example of a spurious state. We can define an initial condition like this. Each neuron Si0 will be the sign of the sum over memory patterns, Pi1 plus Pi2 plus Pi3. Right? So randomly we choose our memory patterns. If for a given neuron 2 of the memory patterns are +1, then we say, okay, that neuron will be +1. If 2 of them are -1, then we set that neuron to -1. So this is what's called majority rule. And we can see that the probability that a given neuron's initial condition under this rule is different from, for example, memory pattern 1. Let's see what that is equal to. So Si will be different from Pi only if from Pi1. Si will be different from Pi1 only if Pi2 and Pi3 if Pi2 and Pi3 align and in the opposite direction from Pi1. So there's a 1/4 chance that happens, right? If Pi1 is positive, then only if Pi2 and Pi3 are negative, only in that case will Si not be aligned to Pi1. We'll use that to calculate the overlap for this state. So overlap with memory pattern 1. Again, 1 over n Pi1 Si0. And now we'll use this fact. So over this sum we have n neurons. 1/4 of them will be misaligned with Pi1. So we have this overlap with memory pattern 1 will be 1/4 times -1 from the misaligned neurons, and 3/4 of the neurons will be aligned. And so that gives us overlap with memory pattern 1 is 1/2. By identical arguments, we'll see that the overlap with memory pattern 2 is similarly, and memory pattern 3 are all 1/2. Okay, so this state has identical overlap with all 3 of the memory patterns. Some kind of bizarre combination of the 3.
Just to understand, what is that majority rule you said?
It's just a way of referring to what I wrote here. So the sign. So we take the sum, and then just apply a sign function. So the sum is positive, it'll be positive. Sum is negative, it'll be negative. And that's equivalent to saying we go according to the majority. Any 2 of the 3 are positive, the sum will be positive. If any 2 of the 3 are negative, it'll be negative.
Is it stable?
So that's exactly what we want to know. Is it stable? So we start out like this, but is this a fixed point? Okay, so that's exactly what we're gonna look at. The possibility that there's a fixed point where M1 equals M2 equals M3, and we'll call that just M star, a uniform fixed point, which is a bizarre thing because we're supposed to have 3 different memories, but we're going to have some kind of simultaneous recollection of all 3 of them. Okay, so I've written our dynamic equations here, and so first of all we'll just jump straight to the fixed point equations for these 3 equations. and we'll check if this is a possible solution. So, from just using the first one arbitrarily, but it'll be identical and symmetric. So we write M1, which is equal to M star, is going to be equal for the fixed point equations to a quarter. Sum over these. Z2 is plus or minus 1, and Z3 is plus or minus 1. Tangent hyperbolic. Beta M star plus Z2M star plus Z3M star. Okay, what do we have in the sum? We have one term that gives us one term where these two are both positive, which will give us 3M. And then we'll have two terms. We'll have two terms where one is positive and one is negative. So those will be two terms where the net. So let me start to write it out already. All here we have one term that's tangent hyperbolic 3 beta M star, and then we have two terms where the net sum of these is plus M. So we have tangent hyperbolic beta M star, and then we have one term where they're both negative, and that'll give us a net negative. So then we'll have a minus tangent hyperbolic beta M star. So the fixed point equation under this assumption of uniformity is M star equals 1/4 tangent hyperbolic 3 beta M star plus tangent hyperbolic beta M star. So that's a fixed point equation under the assumption that M1 equals M2 equals M3. Is there a solution? That's what we want to know. Or that's at least the first part of what we want to know. Okay. So it's kind of a tricky, not so obvious equation. How can we think about it? The first thing that always is helpful is to take limits, right, to get a sense of what's going on. So let's think about the limit of beta towards infinity, just to see what happens. What happens there? In that case, both of the tangents 3 beta M and tangent beta M approach just 1. Well, not exactly 1. They both approach the sign of M star, right? Yeah. Tangent H 3 beta M equals tangent in that limit beta M equals sine of M star. So in that limit we have the fixed point equation M star equals 1/2 the sine of M star. So in that limit, is there a solution? Yeah, there's a solution. What's the solution? Plus or minus 1/2, right? So in that limit, we have a fixed point M star equals plus or minus 1/2. Okay, so already we know that for large beta, this kind of a fixed point exists, a uniform fixed point, and that fixed point will be 1/2, exactly the fixed point that we wrote here, for example, will be a fixed point in the limit of large beta. Okay, now it turns out if we draw the right-hand side, turns out we get something that's qualitatively similar to a tangent hyperbolic, but it peaks here at 1/2 and minus 1/2. And then again, as we're used to doing, the left-hand side is just the identity function, left-hand side. And so as we're used to doing graphically, we can check when such a fixed point exists. It depends on the slope of the right-hand side. If the slope of the right-hand side is larger than 1, then as we're used to seeing, we'll have the three fixed points, if that's the case. So let's check the slope of the right-hand side. So
Now looking at the M of the fixed point,
we're looking now at this equation for finite beta. We got the sense that
why does it sound like time is probability to
Hmm?
be this?
it looks like this. Yeah, that's how it turns out. So let's take the derivative of the right hand side. Three beta m star plus 10 symbolic beta m. And let's do that. And specifically, we want the slope at m equals 0. Okay, so what's the slope of tangent hyperbolic 3 beta m at m equals 0? Let's go back. What's the slope of tangent hyperbolic x? What's the slope of tangent hyperbolic beta x at x equals 0?
1 over cosine of
Well,
0. No, 1. Beta.
Beta.
Yeah, beta.
Beta. That's what it is.
Times 1.
The slope is beta. That's kind of why we call beta the gain function, because it's really beta is the slope at 0. So we get here the slope of the right hand side is just 1/4 3 beta in this case plus beta for this guy, which is of course is equal to beta. So the slope is beta, which tells us what about when does a fixed point exist. So we know this fixed point will exist when the slope of the right-hand side is steeper than the left-hand side. The left-hand side slope is just 1. So fixed point will exist for beta greater than 1. Exclamation point. So that's identical to the condition of our memory. I guess I kind of skipped through it, but our dynamic equation for the memory fixed point that we were interested in, we had m1 dot equals minus m1 plus tangent to h hyperbolic beta m, also had the exact same condition. That fixed point exists, non-zero fixed point exists for beta greater than 1. But we see as soon as beta is greater than 1, we also have the existence of this uniform mixed spurious state fixed point. So that strikes us as a little bit problematic, and we'll have here a similar bifurcation curve as a function of beta. We'll have fixed points at 0 until we reach 1, and then at 1 we'll get this pitchfork bifurcation. We still have a 0 fixed point, which will be unstable, and then we have these non-zero fixed points, symmetric non-zero fixed points that rise up. The only difference to what we're used to seeing is that these kind of max out at 1/2 and minus 1/2. This is a bifurcation curve for these kinds of uniform fixed points, these spurious fixed points. So that, on its face, is not good. The system, as soon as it can learn any memory patterns, will also learn these arbitrary, bizarre combinations of memory patterns. So that's not good. But what should we think about? Is it stable? Are these actually stable? We're used to seeing the case where as soon as we jump into the condition where there are non-zero fixed points, those are also stable non-zero fixed points. But that's exactly what we need to check now. We haven't shown that here. Okay, so to do that, let's now write. Let's try to calculate stability. Okay, so let's try to work out the stability of these kinds of fixed points. So I'll write down the dynamics like this. So we're at a fixed point m star, uniform fixed point, m1 equals m2 equals m3, and now we're going to introduce perturbations to that fixed point. So we're going to introduce delta changes in m1, m2, and m3. So we'll have three equations, delta m1 dot. Delta m1 dot, I'm going to call it delta m1 dot is going to be, let's see, let me take a step back to our original equations. M1 dot, I want to write m1 dot equals f1 of m1, m2, m3, and that f1 is just what I have previously written up here, the full dynamics of m1, and so on. I'll do the same thing for m2 and m3, and now we're going to do the stability analysis. So we're going to expand around the fixed point. So we'll do a Taylor expansion of this m1 in multiple dimensions to give us. We'll have to find the Jacobian effectively, and the derivative of f1 with respect to m1 times delta m1 plus the derivative of f1 with respect to m2 times delta m2 plus the derivative of m of f1 with regard to m3 times the deviation in m3. Okay, so let's calculate these derivatives. The derivative of this f1 function, which we have up here, relative to the three different directions. And these have to be evaluated at the fixed point, of course. Okay, so f1 we have written up here. Solve this guy. That's f1. Okay. What will be useful for us to calculate that is the derivative of tangent hyperbolic, not just at 0. d dx tangent hyperbolic of x is equal to, right, there's a few different ways of writing it, secant squared or 1 minus tangent hyperbolic squared of x. In particular, it's worth noting that the derivative is an even function, right? Tangent hyperbolic itself is an odd function. The derivative is an even function, such that d dx tangent hyperbolic of minus x is equal to, is the same as d dx tangent hyperbolic x. That's going to be an important fact. Okay, so let's see what we get. So the derivative of f1 with regard to m1. Okay, first of all, we have the minus m1 out there, so we have a minus 1 in the derivative. Now, from the whole term, I'll take the derivative directly on this sum term as it is. First thing I'm going to do from the derivative is take out a beta. So I'll have beta over 4. Sum over these same, leave these z terms inside, the summing over plus or minus 1, the 3 is plus or minus 1. And then the derivative of tangent hyperbolic, as we said, is 1 minus tangent hyperbolic squared, beta of the same term. Now, we're taking the derivative with regard to m1. So m1 here only has the beta as a coefficient, so we've already taken care of the beta. So that's exactly what we. So this is it. That's what we get. Derivative m1. We have these z2, m2, and z3, m3. All of that is squared. So okay. So we have four different terms.
Now we have the beta twice, both in and outside.
The beta. So the beta stays around inside as the derivative of tangent hyperbolic beta, and then it also contributes outside by chain rule. Okay, so let's see what we have here. We have the -1 outside, beta over 4. Okay, we're summing over 4 terms. Each one gives us 1, so we have 4. Now, what are we going to have? So we have tangent hyperbolic squared. There's one term where these 3 are all aligned, right? So we have -1 term that's tangent hyperbolic squared 3 beta m. Again, these are all going to be evaluated at the end of the day at the fixed point m star. So we have one term is tangent h squared 3 beta m star. And now what's going to happen here? We have those 3 different terms we saw that have either +1 m beta or -1 m beta. After they go through tangent hyperbolic squared, they're all identical. So we have -3 identical terms that are tangent h squared beta m star, 1 beta m star. It took me a long time to convince myself that that's true. Yeah. So we have one term that's got z2 and z3 are both negative, and so that's tangent hyperbolic negative, overall negative m, but it goes through the squared. So anyway, it gives us a positive, and then we have 2 terms where one of these is positive and the other is negative, so that the net is tangent hyperbolic m. So that's a sum of 3 terms of tangent hyperbolic squared beta m. So that's what we get. That's the derivative with regard to the direction of m1. But we also need to calculate ds dm2. Of this, the same 3. So again, we took care of one term where they're all aligned, and now we have 3 different terms where the sum here is either plus or minus just 1 m star. And basically just saying all 3 of those terms give us identical tangent h squared. That's the point where, by the way, another way to think about it is where we use the evenness of the derivative. So the derivative is even, so it doesn't matter if we're looking at the point plus m or minus m. But anyway, like I said, it took me a while to convince myself that was the case, but it is. Okay, now we also need the derivative of this term relative to m2. Now this time when we take the derivative by the chain rule, we're not just going to get a beta, we're also going to get these z2 terms inside the sum, these plus and minus terms. So let's see what that gives us. First of all, we have beta over 4. And then inside the sum, we have to now keep kind of a little bit more careful track of z2 plus or minus 1, z3 also plus or minus 1. The derivative now by the chain rule, we took out the beta, but now we have 1 minus tangent h squared. Again, same thing in the parentheses. But by the chain rule, after all that, we have to multiply this by z2, which is changing sign. So now, beta over 4. Again, now we have one term where the z's are aligned, and that gives us 1 minus tangent hyperbolic squared 3 beta m, tangent hyperbolic squared. We have one term like that. We have one term where z2 is positive and z3 is negative, so that's going to give us plus 1 minus tangent hyperbolic squared beta m star. and z2 is positive in that term. And now we have two terms where z2 is negative, so we're going to get minus 2. And inside we have the same thing, 1 minus tangent hyperbolic squared beta n. So plus 1 of these terms and minus 2 of these terms. In the net we have minus 1 of these terms. So the result of that is that df1 dm2 is equal to beta over 4. We have the 1s are going to cancel because we have 1 minus tangent squared 3 beta, and then the end minus 1 minus tangent hyperbolic beta m. So we're going to have plus tangent hyperbolic squared beta m star minus tangent hyperbolic squared 3 beta m star. That's it. So that's what we've accomplished. We have the derivative relative to m1, which we're going to call this a. And it's a function of both beta and m star, or through beta also m star, but think about it like that. And then we have the off-diagonal derivative, which we'll call b. It's also a function of beta m star. And these terms will be identical all the rest, right? We'll also calculate df1 dm3 and get also a b. And when we come to calculate df2 relative to m2, we'll get the exact same term there. We'll get that a term, and so on. So we have the net for the net set of equations that are perturbations. Our perturbation vector time derivative is going to be a db bab dba times the perturbation vector itself, 2 dm3. Right? So this is
delta m. 1, you have minus 1. Oh, it's included.
I put in the minus 1. I put in the minus 1. So this is the net Jacobian of the whole dynamic M matrix. Okay. So right to finally calculate the stability of these spurious fixed points, we need to work out the eigenvalues of this matrix, right? Okay. So let's see what we can figure out. First of all, again, let's try to think about it by taking the limits, by taking some limits. So what happens to a this guy over here? Maybe I'll write it again. Okay. So what happens to a in the limit where beta goes to infinity? Well, in the limit where beta goes to infinity, well, let's check when. Let me check that actually. M star. In the limit of, so first of all, we have to keep in mind our bifurcation diagram, right? So here I wrote that a and b are functions of beta and m star, but of course m star, first of all, is a function of beta. So as I change beta, first of all, I'm changing the values of m star. And as beta goes to infinity, m star is equal to 1/2. Right? Is that going to help us?
Doesn't matter. You have a beta outside, so you have one only equals beta, and all the others are like order 1.
But what I have in here is 0 actually in the limit. In the limit of beta goes to infinity, this is -1 and this is -3. And it's so on the face of things, it's not obvious. We have infinity times 0 in the limit. It turns out that the 0 is stronger. Is a stronger 0 than that infinity. So it turns out, and I won't show it, but it turns out that in the limit, that as beta goes to infinity, we have a goes to -1. Okay, and again, also in terms of b, it's not obvious that this is the case. We have infinity outside and a 0 inside. So it turns out that 0 is dominant. So it turns out that as beta goes to infinity, b goes to 0. So at least in the limit where beta goes to infinity, the whole dynamics m goes to basically minus the identity matrix, and the fixed point is stable. Okay, so in the bifurcation diagram, at least we know way out in the ends, these fixed points are stable. Now, let me just draw you guys the pictures.
Why is this good? Because the trace is negative?
Yeah, because the whole matrix is just minus the identity in that limit. So the eigenvalues are all -1. Okay, so let me just show you guys the shape of these functions. Well, let's skip that because it's not even really going to help us figure it out. Okay, so we want eigenvalues. Basically, is what we want to do. So we have this matrix M.
Can I ask something before about this? You said that for large beta it's stable, but doesn't that mean that also for smaller beta it's stable? Because why would it change stability in the middle of the pitchfork?
Oh, that's what we're calculating. That's what we have to calculate. We have the pitchfork shows us where the fixed points, when the fixed points exist. The stability is going to be given by this, right? The stability is going to be given by the eigenvalues. So, I mean, again, we don't know if the eigenvalues are going to be dependent on beta. So they're going to switch signs somewhere along the way. But that's exactly what we're working out. So, in order to do that, we have our matrix. We have to calculate the eigenvalues. Okay, so how do we do that? What are the eigenvalues of this matrix? Any guesses?
The eigenvector 1 on 1.
That's what we love to do. Guess the eigenvector 1, 1, 1. That's the first thing to do for sure. Okay, so let's guess 1, 1, 1. This matrix M times 1.
Is there any, just because we always guess 1, 1, 1?
First of all, because we always guess 1, 1, 1. But also, this matrix has a symmetry, right? All of the rows are effectively identical. There's this kind of shift along the diagonal, right? Right, it's a circulant matrix. It's 3 by 3, so it doesn't necessarily feel like it helps so much to go to like Fourier of 3 by 3. But you're right, it will be identical.
The first vector is
But the first one is exactly the same, right?
So we don't have to guess.
Right. So the circular matrix. So for sure, the first one is the first Fourier vector, which is the uniform Fourier, which is the uniform vector. So that's great. And we can see when we multiply it across the uniform vector, we're going to get every row is just going to give us A plus 2B. So that's great. That's a homogeneous eigenvector with homogeneous eigenvalue A plus 2B. Okay? Now, what else can we guess? Once we've guessed a homogeneous direction, the other thing that we normally like to do is kind of guess the orthogonal directions to that homogeneous the heterogeneous directions. And in this case, there's actually a degeneracy, so you could write them in various different ways. But for example, heterogeneous, we have kind of the change that's uniform, all going in one direction, and we can think about a change that has increasing one overlap and leaving another one unchanged and decreasing the other one. So we can guess this kind of a heterogeneous eigenvector. We'll guess it because it's orthogonal to this first one. And this one will give us, right, we multiply the rows across, we'll get A minus B in the first row, B minus B in the second row, B minus A in the third row, which we can see is A minus B times that same vector, 1, 0, minus 1. So this is, by an educated guess, a heterogeneous eigenvector with heterogeneous eigenvalue, A minus B. Okay, that's 2. And like I said, there's a degeneracy here. So we chose these two neurons. No, they're not neurons anymore. These two overlaps to perturb and leave this one stable. But we could have chosen these two, first one, to perturb and leaving the last one, and that will give us also A minus B. So we have two heterogeneous eigenvectors, and this is similar to a lot of things we've seen systems of size n, where we have kind of one uniform eigenvector with its own distinct eigenvalue, and then n minus 1 eigenvectors in heterogeneous directions that all have the same eigenvalue. And so that's what we see here. And what do these eigenvectors represent? Again, they represent different perturbations from the fixed point. So we're at a uniform fixed point where m1 equals m2 and equals m3, and we're checking different perturbations. One possible perturbation given by the homogeneous direction is just to increase or decrease the overlap. m1 equals m2 equals m3, and also in the perturbation, in the homogeneous perturbation, we perturb m1, m2, and m3 in the same direction. Intuitively, I would say that one feels like the most likely to be stable, but I don't necessarily want to give that too much weight. And then we have these heterogeneous directions, which correspond to different waves, and then with a whole space, a whole plane of different directions where we can perturb the system without changing the average m, but changing the relative weight. So we increase one of the overlaps, and decrease another one, right? And we would like to see if either of these eigenvalues, if they're always negative, or if either of them becomes positive at some point. Okay. So let's see where on the board we want to do that. Right here. I'll need to remember what A is, right? So I have A is equal to minus 1 plus beta over 4 minus tangent h squared 3 beta m star minus tangent hyperbolic minus 3 tangent hyperbolic beta m. And we have B over here. Okay. So we can plug these into a computer. Maybe if I have time, I'll show you what they look like for all values of beta. Analytically, we can't necessarily work out the value of our eigenvalues for all beta. But one thing we can do is expand for beta very close to 1. That's one thing we can do analytically. is calculate lambda homogeneous and heterogeneous for beta very close to 1. Beta equals 1 plus some small perturbation greater than 1. So that's our critical point in the bifurcation diagram, where we know that m, the fixed point, is close to 0. The fixed point is very close to 0, so we'll use that to figure it out, right? So in fact, we won't suffice with just saying that m is close to 0. We want to figure out how m changes as a function of this small beta. So return to our fixed point equations that I probably already erased, or maybe it's behind the board. We had a quarter tangent hyperbolic 3 beta m star plus tangent hyperbolic beta m star. That's our fixed point equation. And we'll expand this using the expansion of tangent hyperbolic around for small 0, right? For small values, because we know m star is close to 0, so we'll use the expansion of tangent hyperbolic x for small 0, which is close to x minus 1/3 x cubed. We're using that beta because it's going to be analytically tractable, because we can use this expansion, and we know that m is going to be small because we've already drawn our bifurcation diagram. So at beta, this is the critical beta, beta equal to 1, where m star is very close. So we're talking about this side of 1, where m star is not 0, but it's close to 0. Because it's close to 0, so we can use this expansion of tangent hyperbolic. So we plug in x minus 1/3 x cubed for these tangent hyperbolics. We're going to get, I'll do a little bit quickly because we're nearing the end, but we pull out these terms as the x, so we're going to get 3 beta m star. The second tangent hyperbolic is going to give us plus another beta m star, and then the minus 1/3 x cubed parts are going to give us minus 1/3 27 beta m cubed minus second tangent hyperbolic is going to give us minus 1/3 beta m cubed. Okay, combining those together, we have at the fixed point for beta near 1, m star equals, this is just beta m, the leading term, beta m star, and then we add together 27 minus another one, right? Oh, right. Oh, yeah. So we have in here, inside the parentheses, minus 28 over 3, and we have a 4 divided by 4 out here. So we just have 7/3 beta cubed m star cubed. Okay. We can combine the m star terms. We have m star beta minus 1. That's our delta beta term. Small. That's small. And that's going to be equal to, in this limit, 7/3 beta cubed m cubed. Again, we know we're talking specifically on the right side of that bifurcation, so m star is not equal to 0. It's going to be close to 0, but not equal to 0, so we can divide by m star and find, and we'll leave it in these terms. It's going to wind up to be useful in these terms, so we divide by m star and find that beta cubed m star is equal to 3/7 beta minus 1. Again, beta minus 1, that's our delta beta, our small term, so that's the leading order of m of the fixed point. That's effectively the leading order of m for small beta. And we're going to use that to calculate the values of a and b at this point, in this regime. Okay. So A in this regime where beta is close to 1, first of all, we'll pull out the 4 divided by 4, so we have out front beta minus 1. Now we're going to need just the leading term of tangent hyperbolic squared. So we're going to use the leading term of that. Use tangent hyperbolic squared of x, which is approximately x squared, just the leading term. There's a following term of x to the 4th, but we're not going to even need that. That turns out. So we have beta minus 1, and then we're going to just use tangent hyperbolic squared is equal to x squared, which is going to give us, so we have minus beta over 4. The first one gives us 9 beta squared m squared, and the next one gives us 3 beta squared m squared. All in all, that's 12 divided by 4 is 3. So we get A equals to beta minus 1 minus 3 beta cubed m squared. And beta cubed m squared, we calculated below as 3/7 beta minus 1. We have 9 plus 3 is 12 divided by 4. Okay, so this term beta cubed m squared is to leading order 3/7 beta minus 1. So we have beta minus 1 minus, now it's going to be 9/7 beta minus 1 or altogether beta minus 1 minus 9/7 minus 2 2/7 beta minus 1. So again, that's our small term. So this is the leading order expansion in A when we're in that regime very close to beta equals 1. And now let's do the same thing for B. B gives us beta over 4, using again tangent hyperbolic squared approximately equal to x squared, is going to give us just beta squared m squared minus 9 beta squared m squared minus 8 beta squared m squared inside the parentheses, and all that gives us minus 2. We have a beta outside, minus 2 beta cubed m squared. Again, beta cubed m squared in this regime is approximately 3/7, so we're going to get that B is approximately minus 6/7 beta minus 1, a small parameter. Finally, now we're getting to our eigenvalues, which is the point of this whole exercise, is to find the stability in those two different directions. We have a homogeneous eigenvalue, which is equal to A plus 2B. So lambda homogeneous A plus 2B. Let's put that together. We have minus 2/7 and we have minus 6/7. It's going to be minus 14/7, exactly 2. Right? It was minus 2. Delta beta, this was our small parameter, so that's negative for that in that regime of beta very close to 1. So indeed, the homogeneous direction close to the bifurcation point is stable. Let's look though at the heterogeneous direction. So that was the value of the heterogeneous eigenvalue is A minus B. So this is going to be, we have minus 2/7 minus negative 6/7, so that's going to be plus 4/7 delta beta. So that, for small delta beta, we've shown that the heterogeneous eigenvalue is actually positive. Right, so we might not have guessed that the eigenvalues will depend so kind of delicately on beta. That once we saw for infinite beta, we saw that they're all negative, but it turns out that the stability changes somewhere along the way of our bifurcation diagram, which I erased, but I'll draw it again. So we know that out here for large beta, we checked already in the limit of large beta, we saw that the eigenvalues were all negative, and the spurious fixed point is stable out here. And now we've shown that here, for very small beta, the fixed point is actually not stable. So somewhere along the way we have another transition, which we won't calculate analytically, but that's in fact what happens if you work it out numerically. And so what this tells us is we have this fixed point that we don't like. We have this spurious state, which is a kind of not really a coherent or functional memory pattern. It's a combination of different memories that are supposed to be distinct. But it's a fixed point, unfortunately. But at least we can kind of have we find some positive outcome, at least, that fixed point is not always stable. So we can think about the gain parameter for very high gain. All of this spurious fixed point is a stable fixed point. In fact, there are many, many, many other fixed points that are spurious fixed points that for high gain, those are stable fixed points of our system, and we're going to remember all kinds of bizarre things. But if we turn down the gain and come back closer to the transition point, then along the way, these spurious fixed points, they lose stability. But remember, the fixed point that we want, our functional fixed point, the memory pattern, that one had the very kind of trivial dynamics of m1 dot equals minus m1 plus tangent hyperbolic beta m1, effectively. And so the stability of that fixed point is maintained all the way to beta equals 1. So as we reduce the gain, we lose these spurious fixed points, and so we're kind of more and more left with just the fixed points that we're actually interested in. So that's good. So the system works. We're not going to have the same capacity. We're not going to have the same maximal capacity as the infinite beta, because that maximal capacity will also bring in all the spurious points. But when we turn down beta, we get rid of more and more of these spurious states, and are left with a functional associative memory system.